So as you can see, as I make this bigger, it stretches it vertically. So I wanted to just look over some transformations because I know this is a topic that students are asking me about all the time. And so what I wanted to do first is actually just kind of go through how they work, which sounds daunting, but the truth is it works the same for all of our functions, whether we're talking about polynomial, exponential, logarithmic, radical, trigonometric, doesn't matter. Whatever the function, they all behave the same way and they all react the same way to parameters. I'll put a link in the description so that you guys can actually go and check this out in Desmos. And you can play with the individuals, but for now, all I'm going to do here to kind of demonstrate it is to go through all of our basic graphs. Now, if you want to look at the individuals, you can open it up. You can see which ones I put. So I put a sine graph, a radical, logarithmic, exponential, and then a polynomial, so that you can kind of see how each of these parameters change all of them. And I guess maybe I'll open up for a second. We can see like here's A. It's always at the beginning of the entire function. And it is our vertical stretch. It will always stretch, compress, whichever way you would like to say it, our function. And it's always going to do it vertically. Now, how do we know that? Well, if you don't believe me, we can always go and play with it here. So as you can see, as I make this bigger, it stretches it vertically, right? If I go between 0 and 1, it compresses it. It squishes it together. If we make it negative, it turns it upside down. There's your reflection as well, okay? So we'll put that back to 1 for now so that then we can look at another parameter. So then if we look at B here, B is always going to be right before the X, okay? And this is our horizontal stretch. So if I look at this one, when I make it bigger, it's making it smaller. Now, why is that? Because B is weird. Everything that happens to X is kind of counter to what we would normally think. And so in reality, what's happening here is that we are compressing this by a factor of 2.5, not actually stretching it, okay? Likewise, if we put it between 0 and 1, there we actually see that it is pulling it apart. It's making it bigger, okay? And again, if we go negative, we simply take all of them and flip them, right? This time, however, we're not flipping them vertically, we're flipping them horizontally. So it is a reflection in the y-axis. All right, let's look at C. So if we look at C here, C is always attached to X. That means it's going to move things horizontally for us. If you're talking about trig, you might hear it called a phase shift, but it's always moving it horizontally. Now, what you'll notice here is that this is minus C. What that means is that once again, X is weird. It's going to do kind of the opposite of what we might expect. So if we make this into a positive, like positive 3, you can see it actually moves it 3 units to the right, not to the left, even though it's going to be written as X minus 3. Likewise, if we put it as negative 3, well, it's X minus negative 3, which of course means that it's going to actually move it to the left here. So it's always kind of doing the opposite, even though it's going to be written as, once again, X plus 3. So it looks kind of backwards to what you would anticipate, okay? But we can see here that every single one of these graphs is just moving horizontally, okay, when I change C. So it doesn't matter what graph we're looking at, C is going to move things horizontally. Last one here, of course, is D, this one that's kind of outside of everything, written at the end, okay? And this one here, the only thing left, of course, is to move it up and down vertically. So this one literally moves all the graphs vertically or moves them all negatively. And once again, for this one, it doesn't really, well, it doesn't do anything weird, I guess. It just moves it, right? If I put it at 3.2, it's moving them all up 3.2, right? If I put it down, it's just moving them down 3. It's not doing anything strange. So hopefully that gives you a bit of an idea, refresher, crash course, whatever you want to call it. If you'd like to, like I said, go check this out. Go look at each one of these individually. And real quick, I just wanted to apply it to a couple of questions now for you, just so that you've got a couple practical examples of how we might do this. So in here, I've got a couple of diploma level questions for Math 30-1. However, these would apply to many other math courses, not simply to the courses here. So we've got a function drawn here. The function is f of x as defined by our question. It's firmly in quadrant 2, as we can see. It's some sort of probably trigonometric function because it looks very sinusoidal. And then it's got a very restricted domain, of course. And so when we look at this, the reason they're doing that is just so that they can check whether or not we understand our transformations. Okay, and then what they're going to do is it's a numeric response question. They're going to give us a bunch of transformations using those A, B, C, and D, and see if we can figure out which of the 4 quadrants it ends up in. Okay, so if we go down here, maybe I'll zoom out so you can kind of see graph as well. Okay. For each function below, identify the quadrant in which the graph will be completely drawn. Okay, so if we've got f of x minus 8, that minus 8, that's outside of everything. That would make it a d value, which means that's moving the entire thing vertically. Because it is minus 8, it's going to move our entire thing down like this, right? So if it moves it down 8, we can see that even this highest point up here, which is around what, 1, 2, 3, 4, 5, 6, is going to come all the way down to -2. So it's going to be somewhere in here. So it's still going to move that entire thing down. The whole question will now be in, or the whole graph, I should say, will now be in quadrant 3. Okay, so that would be our first blank there. I'm just going to make this a little bit thinner here so you can see it better. And maybe I'll use a different color actually for each one. Okay, so for our next one here, now we're looking at what if we put f of x plus 8. So first thing you'll notice, this is inside of it, and therefore it is in such a way that it is our c value, okay? I'm realizing if this looks a little bit strange as to like why I'm noting that this is c, that's d, because before I gave you specific examples. If we write it in function notation, which maybe we'll just do real quick down here, right? Then what we're going to do is we're going to get that it's a f of b of x minus c plus d. Okay, and that would be like, regardless of what kind of function we have, we can still see a's vertical, b's horizontally stretching, and then we've got our movements. So c is moving it horizontally and d moves it vertically. Okay, so because these are generic functions, they're not actually telling us what it is. I just wanted to put it in here as such. So here we can see this is most definitely a c, and while it does look like it's 8, it's not moving it to the right. Okay, it's actually moving it off to the left, right? Because it's written in the form x minus c. So to get that positive, we have to put in a minus 8. And if we go and look at our graph up here, if we were to take that whole thing and move it to the left, it's going to stay in quadrant 2. It's not going to change anything. So that means that over here, we're going to remain in quadrant 2. Now, for our last one here, we're doing the graph of m of x, which is going to be f of negative x. This is a b value right here. It's because it's in front of the x, okay? And it's just a -1. So all it's doing here is actually reflecting it. And what we need to remember is that reflecting it in the y-axis, thereby moving it horizontally, or is it flipping it in the x-axis? Can be a little bit tricky to think about this. If you're really having a hard time, use a test point, right? If I were to put this point in, this is going to be at x equals 2. It's hard to see that. Let me make that smaller again. There we go. This would be at x equals 2. Well, if I put a negative in front of it, it's now going, sorry, it's at -2. It would be -2, and it would be at 2. So it's actually going to flip it over here, which of course is a reflection in the y-axis, okay? So it reflects in the opposite. If the negative's in front of x, it moves in the y-axis. If it's in front of y, it moves in the x-axis. So this one's going to flip it over here, look something along these lines, and so therefore it's going to be firmly in quadrant 1 there. All right, so that would be our first question. After this, what we're going to do is we're going to just look at another one where we're actually putting in some of these values and figuring out where they would go, a, b, c, or d. Okay, so we've got the graph of y equals f of x. It's stretched vertically by a factor of 1/9. Okay, so what I like to do with these is if I've got something like this with my students, I immediately tell them, write it down, man. Right? If it's a vertical stretch, that means that's an a value. Okay, it's stretched horizontally by a factor of b, of 1/7, which is b, and then translated 8 units down, that would be a d because it's moving down vertical. These transformations can be described by mapping notation. Okay, so this time instead of putting it in a graph, we're going to look at mapping notation for it. So our m value here is the stretch, right? It's what we're multiplying x by. So that one was 1/7 if we look at it, okay? So this would be our first one here. So reference number 1, going to be first. Then after that, we're looking at n. N is our vertical stretch, so it's the thing we're multiplying it by vertically, because of course this is x and then y, right? So it's multiplying it by y. So that would be reference 2. And then our last term here is the p. That's the one that we're going to be moving it up and down. So it's right here, 8 units down. Now keep in mind, if we're moving it 8 units down, that's going to mean that it is -8. not 8, right? And so that would be our values that we need to now put in. And so putting mn and p in respectively, it's going to be reference 1, 2, and 6, meaning that we're writing in the function where we're doing that mapping notation by a 7th, then by a 9th for y, and finally moving it 8 units down. All right, guys, I really hope that was helpful. I'll be putting up a few more of these. And by all means, please check out that Desmos tool if you're having a hard time figuring out how these things are moved around. It'll really help you just be able to understand that regardless of what the function looks like, A, B, C, and D are always doing the same thing. All right, see you guys later.